Greetings from Engineering Tomorrow studio and headquarters. We are recording today in St. Louis, the gateway to the West, heartland of America. I'm your normal host, Brian Gomski, and today we are bringing you Water Source Heat Pumps 101. Our teachers today are Dan Bilancia of ClimateMaster and Ryan Miller of Midwest Machinery, Kansas City. So sit back, relax, and prepare to get plugged in to the HVAC matrix. Cue the intro.
Broadcasting around the world. This is Engineering Tomorrow, the podcast committed to bringing you the best in commercial construction, design, and engineering from the brightest minds in the industry. This is the stuff they don't teach you in school. So sit back, relax, and open your mind. You're about to get the insider knowledge to improve your next construction project or advance your career. This is Engineering Tomorrow.
Today we have with us Dan Bilancia, who's the ClimateMaster Regional Sales Manager. Dan, how's it going?
It's going well. Thank you for joining us.
So we're going to go ahead and get right into this. Dan's here to talk about ClimateMaster water source heat pumps and some of the system configurations that are out there and the advantages, some of the efficiencies that can be gained.
Well, good morning, everybody. My name's Dan Bilancia. I'm a regional account manager with ClimateMaster. For those of you who are not familiar with ClimateMaster, we are a manufacturer of HVAC equipment with the longest tenure of any other manufacturer in the water source heat pump industry. Our operations began in 1957. And our heat pump and our DOAS product lines are designed, tested, and assembled under one roof in Oklahoma City, Oklahoma. All of us appreciate you taking the time out of your day today to attend today's webcast. We have an excellent topic to cover, proven technology that has been applied successfully in commercial and residential applications around the globe for decades. That technology is water source heat pumps. Due to their many advantages, water source heat pump systems are a popular choice for commercial buildings requiring multiple zones of temperature and humidity control. Owners, architects, engineers, and contractors face many challenges in the design and construction of buildings today. Challenges such as balancing building aesthetics with function, indoor air quality, energy efficiency, and sustainability come to the forefront of the design process. Let's consider today's webcast as an entry-level college course. In this short hour, our goal will be develop a basic understanding of a water source heat pump system. The advantages of a water source heat pump system extend from architects, engineers, and contractors all the way to developers, owners, and end users. One of the major advantages of a water source heat pump system, one that I'm sure we're all familiar with, is the ability to simultaneously heat and cool different zones in a building. But what if our building doesn't require zoned temperature control? What other advantages does the system have to offer over other conventional HVAC systems? For starters, a water source heat pump system provides the building owner year-round reliable performance. ASHRAE estimates these systems to have a 20-plus life expectancy, and due to its redundancy, when one unit fails, the rest of the system will remain operational. Another point for water source heat pumps is its lower upfront installation cost and their energy leading efficiencies. Did you know water has 3,200 times more specific heat capacity than air? Now, what does this mean to me? Well, I'll tell you. It means two things for me in the water source heat pump systems. Number one, I can move as much cooling in water in a 2-inch piece of pipe as I can with air in a 24-inch square duct. And because of this higher thermal capacity of water, we're able to make the heat exchangers for our water source heat pumps a heck of a lot more compact and far more efficient than an air-cooled heat exchanger. This allows ClimateMaster to provide the industry with a more compact overall unit footprint and some of the industry-leading EERs.
So, Dan, I want to make sure I heard that right. You said you can move as much cooling in a 2-inch pipe as you can in 24-inch duct.
That's in water, yes. So you can move as much cooling capacity in water in a 2-inch pipe as you can with air in a 24-inch square duct.
Yeah.
So if you're thinking about this, thinking about the size and spacing and everything else like this, you're riding a duct, you run duct runs. Now that we're eliminating these large duct runs, you're able to make the ceiling higher. You're able to you're making that building envelope, that internal space, larger. And moving forward, you can see with other things that we do with ClimateMaster on how that relates to opening up the space, ease on the installation, and lower those costs. As I mentioned, we're able to create a heat exchanger that is much more compact than an air-cooled heat exchanger. So with these compact designs, what ClimateMaster does is we offer these designs in an array of tonnages and different configurations. And on top of that, these units are completely assembled and tested from the factory. And typically, when these things are built at the factory, our reps, our customers, our contractors, they're actually requesting that they have all the necessary zone level controls installed, as well as any hydronic accessories installed as well. The typical capacity of these things, like I mentioned, we have an array of tonnages. The tonnages that you typically see installed for water source heat pumps range from one half ton up to 5 tons. So what does this all mean for us in the lower cost of installation and our flexibility of design and so forth? Well, because of these relatively small packaged units, what we're able to do, like I've already mentioned, we greatly reduce the duct runs. So we're able to heighten ceilings. We're able to tuck away these units up into a closet. There's actually times where the duct runs are actually non-existent on systems like console units or vertical stack units. Also with water source heat pumps, if we start thinking about, we go back to that comment about simultaneously heating and cooling. If we think about some of those other systems that can actually simultaneously heat and cool, we have a 4-pipe VAV system. Now, they can heat and cool. However, they're going to require 4 pipes. The water source heat pump system on a traditional system would require 2 pipes, and we can also do it in a single pipe. So right there, we're cutting out labor and material to hang out the pipe for the water loop. The other systems that are able to do a simultaneously heat and cool is also a large air-cooled VAV rooftop system. As I mentioned again, we can move a lot more cooling in 2-inch piece of pipe than we can in a 24-inch, or the same in a 24-inch piece of duct. So with this large air-cooled VAV system, you're going to see a lot of duct runs, large duct runs and drops throughout your building, eating up some of that usable space and rentable space for the building owner. The other system that we're able to simultaneously heat and cool is your variable refrigerant flow, or VRF. These VRF systems are excellent at simultaneously heating and cooling. However, they're not applied. They should be applied to absolutely every building application. Some of the advantages, or one of the advantages of water source heat pumps over a VRF system is the limited amount of refrigerant in a water source heat pump system. All of our refrigerant is contained right there in the package unit, in the heat pump itself. So if there's a leak, it's a small leak. It's not a lot of refrigerant. Plus, it's extremely easy to find because we know where it's at. It's at the unit. With a VRF system, what you're looking for is you're looking for a confusing, complicated maze of refrigerant lines to find that leak. Plus, you have an extensive amount of refrigerant running through the buildings and different rooms, et cetera. These are all things that are going to require the architect and engineer to understand local codes with the amount of refrigerant in a certain building size. I've talked about lower install costs and how we managed to do that with having more units, smaller duct runs, et cetera, and these units also being completely factory tested and coming with the necessary hydronic accessories from the factory. So this also cuts back on having to put a control valve in the field or anything else like that. Some of the variations that we offer lend to the architect and the engineer. And we're talking about design flexibility. And with these array of tonnages, configurations, and the compact of the footprint, the engineer is able to conceal these heat pumps in individual spaces, helping them to more easily zone the building. So we can put a water source heat pump in a zone above the ceiling in a horizontal position. We can put it in a closet in a vertical position. We can tuck it below a windowsill. We can put it in a stairwell. We can recess it into a wall, as similar to like a vertical stack unit and a high-rise application where the floor-to-floor layouts are similar. And then each zone can then be sized down to a minimum of 200 square feet and as large as thousands of square feet. So with all these options that we have from ClimateMaster with the different tonnages, the configurations of heat pump, this really lends to the architect and the engineer not to sacrifice on building internal aesthetics. The design flexibility also extends into the upfront installation costs for building owners. A large portion of this system installation costs are deferred to the time the tenant takes the space. So we don't necessarily have to have the heat pumps in place while we're building this, while we're finishing out the space. The heat pumps themselves represent probably about 50% of the total install cost. So the owner can actually hold on to purchasing these heat pumps until they actually have a tenant-signed lease, therefore improving their cash flow throughout the construction process of this building. One last point that I'd like to touch on before we move on is the EPA states that the average American spends 87% of their time indoors. That means quality of air is as important as the actual temperature. Designed for compliance with ASHRAE standard 62.1, ClimateMaster offers a line of DOAS units to ensure ideal dehumidification at all ambient temps. Our systems and our controls are designed to limit space relative humidity to 60% or less during all load conditions. The reason why I bring this up is if you're familiar with water source heat pumps, we need some form of ventilation system. One of those ways to accomplish this is with a dedicated DOAS system. Some of the things I was discussing about the benefits or advantages of a water source heat pump system is we're able to simultaneously heat and cool. We have reliable performance. We have extremely flexible zoning capabilities with our different tonnages, our different configurations of the product. We're extremely energy efficient. And later on in the slides, we'll show you the operation of a system through the winter months, the summer months, and also the shoulder seasons. And you can understand how this system can even be more efficient as well. We discussed how it could assist with lowering the cost of installation. And we discussed about indoor air quality as well. At the start of this, I said this was going to be an entry-level college course. So here we are. We're jumping into an entry level of a water source heat pump and its operation and its components. So a water source heat pump is a mechanical device to transfer heat from one medium to another. A water source heat pump utilizes water to extract heat from when we're in heating mode, and we reject heat too when we're in cooling mode. The operational water temp has a wide range for water source heat pumps, and it's typically kept between 60 to 90 degrees. The refrigeration circuit of a water source heat pump consists of the following components. We have a refrigerant to water heat exchanger. This heat exchanger can be a tube and shell, or a brazed plate design. ClimateMaster utilized the tube and tube, also known as a coaxial refrigerant to water heat exchanger. The second is a refrigerant to air heat exchanger. This is a fin tube coil similar to any DX coil on an air-cooled rooftop. The third component is a compressor. All heat pumps have at least one compressor, depending on its capacity. Compressor type and size all depends on the manufacturer and their performance requirements. ClimateMaster offers three different choices for we offer a single-stage compressor, we offer a two-stage compressor, and we also are rolling out a variable speed compressor for commercial applications as well. With our variable speed compressor, we can dial down the capacity to about 30% of its capacity. Along with that variable speed compressor, we have things like an ECM fan motor and a modulating valve and pump as well in the unit. The fourth option, or the fourth component of a water source heat pump, is the expansion device. Most commonly used is a thermal expansion valve, also known as a TXV. This device meters the quantity of refrigerant flowing through the cycle to meet any load requirements. And last but not least, what makes a heat pump is the reversing valve. This device allows the two heat exchangers to act as an evap or a condenser, allowing the unit to provide either cooling or heating to the space. During the cooling mode, heat is extracted from the air by evaporating the refrigerant into the refrigerant to air heat exchanger. Hot gas from the compressor enters the refrigerant enters the refrigerant to water heat exchanger. In the cooling mode, the refrigerant to water heat exchanger acts as the condenser. In the condenser, the refrigerant condenses into a liquid refrigerant as it rejects heat into the cooler water passing through the heat exchanger. This liquid refrigerant then flows through the TXV, which drops the pressure of the liquid refrigerant. The cold liquid vapor mixture enters the refrigerant to air heat exchanger, and in the cooling mode, the refrigerant to air heat exchanger acts as the evap, as I've already mentioned. The indoor air is cooled and conditioned to the space. The cool refrigerant vapor travels back to the compressor, where the cycle repeats itself. In the heating mode, the refrigerant circuit is reversed. The refrigerant to water coil now operates as the unit's evap, and the refrigerant to air coil acts as the unit's condenser.
You're listening to Engineering Tomorrow, always striving to bring you the best in commercial construction, design, and engineering.
So now that we have a very basic, and I know I went through this quickly, basic understanding of a water source heat pump's operation, what are a few advantages of the system itself? All right, water source heat pump system components and their function. As the most, you're going to hear me say this throughout the hour, and I apologize, and I'm going to repeat myself as the most energy efficient HVAC system on the market, water source heat pump systems are uniquely simple in design. As we discussed, heat is moved through an interconnected water pipe loop and either rejected through a cooling tower or put to work in space. Other items, I'm just talking about life expectancy here, is 20 plus life expectancy. Other things like compressor technology, electronic controls that have more protection, air coils, and coaxial heat exchangers, stainless steel drain pans, all these technologies are actually furthering the life expectancy of equipment and making it more efficient. So let's jump back into the major components of a water source heat pump. Obviously, heat pump. We've already discussed the heat pump. One of these heat pumps is actually going to be placed in every zone of the building, or depending on how you're going to decide on how you're breaking up the building zones, each heat pump supplies the zone. Other component is the loop piping. This loop piping is what carries water to and from the heat pumps and connects the individual components of the system. Piping can be a traditional two-pipe system or a single-pipe system, as I mentioned. Careful planning of this water pipe is important, as it is about 25 to 35% of the installation cost of the system. Two-pipe systems can be arranged in a direct return configuration or a reverse return configuration. So I know I may have confused you with different configurations. On a standard traditional two-pipe system, we have a supply pipe and a return pipe, which is the standard two-pipe system. We can also do a single pipe application, which we have a whole nother presentation concerning single pipe applications as well. But that single pipe will actually act as the supply and the return for the loop. And then on a two-pipe system, back to the two-pipe, I apologize, we can configure that return in two different ways. And one way is a direct return, and the other is a reverse return. The other component is a loop pump. Now, the loop pump is a critical operation to the system. The pumps are installed downstream from the tower and the boiler and upstream from the heat pumps to ensure positive water pressure throughout the entire system. The system pumps can either be constant or variable flow pumps, and there's other options for pumps as well. If you have questions about pumps or would love to learn more about pumps, please contact Ryan Miller at Midwest Machinery Company. They have a lot of pumps, and they can work with you guys on your next project. The other component is we need to have a heat source in our loop. A heat source is used to maintain system water temperatures above 60 degrees. Typical heat source for a closed loop water source heat pump is a hot water boiler, and this could be either gas or electric. The fifth component is we need to have some way to reject the heat. So we have to have a cooling source or some type of heat rejector. So that last is the heat rejector is used to maintain the system water temps below 90 degrees. So we have the boiler, that's helping us maintain above 60, and then the heat rejector is helping us maintain it below 90. A typical heat rejector for a closed loop system is a cooling tower. Now, the goal is the system. We want to educate everybody on the system and its benefits and so forth. Right. And the last piece is the controller. We need a controller to actually maintain that system loop. So it's monitoring the temp of that system, the flow, the pressures, etc. So it's controlling the boiler. It's going to be controlling the cooling tower and the pump and so forth. So as those temps vary, the flow varies, that's what the control is doing.
Can you remind me real quick, what are the different return piping configurations?
Two return pipe configurations. We have a direct return. Just to kind of explain that real briefly, is basically the return will travel in the same path as the supply, to kind of sum that up. And then we have a reverse return where basically the water travels an equal distance in the supply and return for every heat pump. I don't have an image. It's real easy to show as an image on that one, but hopefully that kind of clarifies what I mean by that.
I think that makes sense.
So far through our time together, we've discussed the advantages of water source heat pump. Not all of them, because I've been jumping all over the place trying to make this all fit. So we've got the advantages of water source heat pump figured out. We've reviewed the components of a heat pump itself and what their functions are and what makes a heat pump a heat pump. We reviewed the major components. Of course, there's other components within the system, but the major components of a water source heat pump system and what their functions are. And I've discussed a lot about energy efficiency, et cetera. So what we're going to review is some of the operation and how this unit or how the system would actually operate in different seasons of the year. So up on the screen, real simple, we have a summer operation. All the zones in the building typically will require cooling. So what happens when our heat pump is in the cooling mode, it's dumping warmer water back into the system loop. And again, our operational range for a closed loop traditional water source heat pump is 60 degrees to 90 degrees. So as we're dumping warmer water and all these units in the building are operating in cooling mode, every unit is dumping warmer water back into that loop, raising the temp. So we need to put this heat somewhere. So what's happening is the cooling tower on the system is running and it's rejecting that heat. The boiler is off. I have too much heat. I do not need any more heat. The boiler is not running. So in the summer months, like I mentioned, the only thing that we're going to be needing to run is your cooling tower and your pump to circulate the water. In a winter operation, in winter warm-up, let's just say water actually retains the heat rather well overnight. So in an unoccupied time, the system shuts down. There's still going to be some heat in that system piping, but in the morning, most likely in the winter, every zone in the building is going to require heating. So what's happening is, like opposite of that summer operation, all the heat pumps are in heating mode. And when they're in heating mode, we're dumping a cooler water back into that system loop. Again, we want to maintain that system loop between our operational range between 60 and 90 degrees. So since we're lowering that temp, we want to make sure it stays above 60 degrees. So what are we doing? We're turning on that boiler when necessary. So the controls is monitoring the temps, the flows, and everything else. So as those heat pumps are operating in heating mode and dumping cooler water back into that system, we're dropping the temps of the system and the boiler's kicking on to maintain those temps and keep it above 60 degrees. Another operation is we have a winter warm-up, an occupied mode in winter, since I just discussed winter warm-up, and then occupied mode in the winter and occupied mode in the shoulder season, fall and spring. In the winter, occupied mode in the fall and the spring, most likely the external portions of your building are going to require heat. These units are going to be running in the heat mode, and what's it doing? It is going to be dumping cooler water into the system loop. Now, the internal of the building may not require any heat. In fact, it may require cooling. So these units are actually set and they're running in cooling mode. So here we are simultaneously heating and cooling our building. We're dumping cool water into the loop, and we're also dumping warm water back into the loop, hopefully self-balancing that temp where we're not having to run the cooling tower or the boiler. We can go even further
to me, this is really where water source heat pumps knock it out of the park. This is where they really earn their reputation for energy efficiency. This is a unique and extremely beneficial scenario here that we're talking about.
Absolutely. When it comes down to heat recovery, it's the system loop inherently absorbs heat. So when we're moving it from one portion of the building to the other, we do it very easily. So we're not rejecting heat. We're not wasting heat. We're using it in another portion of that building. I live in a condo in St. Paul. I'm on the top floor, and my system is a VAV system here, and I'm talking them into upgrading it to a water source heat pump system, and we're probably going to do a single pipe application because it is a 6-story building. But long story short, I have a VAV system here. I'm on the top floor. And all winter long, I keep my windows open because I do not need any heat. Everyone below me and around me are cranking those VAV units. It's hot. I remember one day I had the windows open. I had the door open into my apartment so I can have air going through. And one of the board members of the association came through and says, "Hey, Danny, what are you up to?" And I said, "Oh, I'm just wasting energy." And that's what I did. And I finally had I had his attention, and he asked me to come to one of the board meetings and present water source heat pumps and the systems and how we can move this building over to a water source heat pump system so that we can simultaneously heat and cool in the building, because they get a lot of complaints about people such as myself on the top floor, always hot. And as of right now, it's probably about 65 degrees outside of Minnesota. I'm on the top floor. The building is a two-pipe system. So it's a two-pipe VAV system. I'm waiting for it to turn over to cooling. I'm sitting here with my windows open and I have a fan hitting my back. I am hot. It's hot in my building, and it's 65 degrees outside. So anyway, another advantage of a water source heat pump systems, you're right, 100%. They move heat from one area of the building to the other. Sorry for my own little story there.
No, I
just love complaining about my VAV system because I am right now sweating.
I mean, we love real world examples, and it really drives it home. So absolutely.
Yep. You know, the one thing about it, and I'll give it a plus, I don't hear it running. When it is running, and I very rarely run the system, it is quiet. It is a nice unit. So I give them credit for that. All right, so moving on. Up until now, we've covered the traditional closed loop water source heat pump with a tower and a boiler, acting as our heat rejector and our heat source respectively. However, some water source heat pump systems can be provided as a towerless or a boilerless system. How do I do this? Well, these systems utilize the Earth's natural thermal properties to maintain the system loop water temp in the operating range. Remember, I keep saying 60 to 90. Well, with a geothermal loop, we can extend that down to 20, and I want to say it's 20 degrees or 30 degrees to 120. I'll double check myself. And we make some changes to the heat pump by insulating a few of the lines and the condenser inside, etc. So these systems, when we're using it, if we're using the ground thermal, these systems are recognized as the most energy efficient. Now, I've said that like 10 times today, but this is the most energy efficient and environmentally friendly HVAC system available to the market per the DOE and the EPA. These systems are referred to as ground source or geothermal heat pump systems. And can be provided in several variations depending on a few of the site characteristics. We'll quickly review some of the additional benefits of ground source and their different variations, and why an engineer may choose to use one of these different variations over the other. So right off the top, you've heard me say it. I'm all about efficiency, efficiency, efficiency. I've been stating it. We're the most efficient system out on the market, while adding a ground source increases the efficiency even more by using a renewable energy to maintain our loop temp, and it's actually free. You can pull heat out of the ground for free. The installation of a ground loop also eliminates the installation of a boiler and a tower. So potentially, we can eliminate all equipment to the exterior of the building. We may still need a ventilation system, of course, but we can use an indoor DOAS system. We can remove all the boxes and all the mechanical equipment from the exterior of the building, helping out with the building aesthetics for the architect and allowing that architect to really mesh that building around with its environmental surroundings. Also, if we include a ground loop, we don't need all those controls, right? So the controls that are going to be providing the heat from the boiler or the cooling tower, we can eliminate some of those loop temp controls. We also reducing the size of that mechanical room. Keeping in mind, the only thing that we need now, since we removed that tower and also the boiler, we only need a mechanical room that can house the pump. So again, we're reducing the space for the mechanical equipment and giving that architect and engineer more usable, profitable space. If I was a building owner and I had a high rise, obviously I want to try to squeeze out as much square feet out of something so I can get more money for space from a building renter or something like that. So what are the different types of variations? Geothermal earth loops come in several different configurations depending on the space availability and certain soil properties. Loop fields can be located under parking lots, landscaped areas, or a number of other locations that you may have on your building land. All loops are high-density piping to circulate either water or the antifreeze mixture. The joints are connected fittings are thermally fused, so we can prevent leaks or anything else like that. And typically, most piping arrangements have about a 25-year or longer warranty as well. Now, first up, what we have is vertical closed loops. Vertical closed loops use boreholes drilled to an average depth for about 250 feet. Once the loop pipe is inserted in the bore, it is grouted for maximum thermal conductivity when the space is limited. When space is limited on site, vertical loops are most common type of geothermal loop installed. Next up is the horizontal loop. So here, we're not going down 250 feet. We're actually just using on the horizontal surface of the land. We're going down a few feet, of course, to about 4 to 6 feet. But we're now running these loops instead of vertically, we're running them horizontally. ClimateMaster actually has a horizontal water source heat pump loop in our parking lot. So if you ever come down to ClimateMaster in Oklahoma City, you'll see this massive parking lot. You'll know below that you have our ground loop for our water source heat pump system providing our building.
And so, Dan, what are some of the main drivers that would push you towards either a vertical loop versus a horizontal loop?
So with the vertical loop, and you're going to have limited spacing, right? Because if you're thinking about it, you're going down 250 feet, right? And you're going to need multiple wells. And I'll double check myself. And we also have software at ClimateMaster to help size these well fields and design them. But I want to say it's about 200 to 300 feet per ton. And I'll double check myself. Please don't quote me on that. I don't design fields, but we do have the software and capabilities to help assist with that. With the horizontal, as I keep on mentioning, is to answer your question, I want to say space, and also cost. When it comes down to the horizontal loop, it's actually one of the most cost-effective loops that you can install because you're not going down. You're kind of just skimming that top. Yeah. And they're typically found in the open fields or in parking lots or in parks is what you see. If you think about schools have a lot of land, right? So schools have football fields, baseball fields. They can do you'll see a lot of geothermal applications in public schools as well. The next loop that we have described here is a lake loop or a pond closed loop. This is actually one of the most cost-effective systems. This is say we have a water feature nearby. We have a pond or a lake on our property. Well, we can utilize it. And we can actually utilize it in two ways. We can utilize it in a closed loop, and we can put a heat exchanger into the water at the bottom of the pond or the lake, whatever it is, as shown in the visual here. The loop is very similar to the ground loops as well, but again, it's just sitting in the lake. If we have other body of water or some other type of feature nearby, what's also most commonly known as an open loop or a groundwater system. These actually use nearby water and it's an open loop, so it's not closed. What it does is it'll take water from the lake or any other nearby type of water from a well, and we'll discharge that water back into another body of water. Groundwater systems usually employ a plate heat exchanger inside the building in order to keep that water loop and the building water separate. This prevents any contaminants from affecting unit performance and extends the life of our system. Groundwater systems are often the most efficient as the groundwater is always at the same temperature year round. What I really just wanted to kind of point out, what you see on the screen here is just, make everybody aware that there are federal tax incentives for geothermal, and it doesn't necessarily have to be 100% full geothermal. We can also do hybrid systems where we may have a tower connected with the geothermal or maybe even a boiler connected with the geothermal. But the commercial tax credit will remain at 10% through 2021. This new bill also changes placed in service language to the tax code, construction to which begins prior to 2022. So think about this. They're extending it. So say we're not starting construction until December 2021, but I do have a water source heat pump. As long as they start construction prior to January 1st, 2022, they can experience those rebates for a geothermal system. Now, I will have to read into it. We have some more of this information up on our website at ClimateMaster.com. We have the tax incentives online. But I do want to say it does apply 10% to anything that actually touches that geo loop. So for thinking about it, we're looking at like supply diffusers, all the duct work, anything that's running off that geo loop, maybe even the pump, the cooling tower is 10%. So we've talked about variations. I've got about 15 minutes left, and we'll get through this very quickly. I don't want to bore you. So far, we've gone through a very traditional water source heat pump system with the boiler and the tower. We discussed the water source heat pump itself, its components, its functions. We talked about the overall system very briefly, its different components, and we've also discussed the different variations in it where we can actually, instead of doing a boiler tower, we're actually going to use the ground as our heat rejector and also our heat source. Well, another variation that we can do is that we can actually combine a geothermal and a traditional water source heat pump system. And some of the reasons why we may want to do this is, if you think about it, one of the disadvantages of a geothermal heat pump system is the upfront installation cost and the size of that geo field. That field can be extremely large and it can be extremely expensive to size depending on the size of your building. You have a very large building, you're going to have a very large field, and that installation is going to increase significantly. So what we do is when you have a cost issue, but you still want a water source heat pump, we do have some land, we can utilize it. So why not utilize a hybrid system? What I mean with a hybrid system is we're actually going to pair up a geothermal system with a traditional water source heat pump system. Now, what the benefits of this is that we're able to reduce the size of the geo loop. So we're reducing the size by only sizing that geo loop to handle one load. It's going to either handle the cooling load or it's going to handle the heating load. Typically, 365 days out of the year, the more demanding load in the building is going to be the cooling load. So we're going to size that heat pump or that loop for the heat load. So we can keep that cost down, and we're only going to be using the Earth's thermal energy for our heating in our building. We'll pair that geothermal system with a cooling tower, and the cooling tower will act as our heat rejector. So we actually do have two heat rejectors. We'll have the ground source, which actually can absorb heat, and we'll also have that tower. So like I said, the advantage of this is we're able to make this a lot shorter or smaller and less cost for the geo loop while still maintaining all those efficiencies for our heating and using that free heat. And we're making it smaller, we're making it just less expensive. In the summer mode, we're rejecting heat into the ground, and we're also using the cooling tower to reject heat. And then in the winter operation, again, we don't have a boiler. So we remove the installation of a boiler, the maintenance of a boiler, and the mechanical room, or the space required in a mechanical room for the boiler as well. So what we're using that ground thermal energy for all of our heat in the system, because we size that ground loop to only handle the heat requirement in the building. I'll briefly go over an example that we did for the Tulsa Oil Company. They had a 200 square foot building. They required 750 tons of cooling. The system would have cost them about $450 million. They required about 500 boreholes for their geo field. They were 300 feet deep. Like I mentioned, each one was 250 to 300 feet deep. One 300-foot deep borehole provides 1.5 tons of heat rejection. The well cost to size this well for both cooling and heating would have cost them $1.2 million. So where this is in Tulsa, Oklahoma. As you're all familiar with probably the climate down there, it's probably very similar to Kansas City, that the majority of the load is going to be cooling. So what they did was they requested that we size the loop for their heating load only. We installed the closed loop with the cooling tower and sized that loop for the ground loop for just the heating, and we reduced the number of boreholes in the entire system. It went from 500 all the way down to 150 by adding that cooling tower. They also received the federal tax credit of 10%. They reduced the geo wells, right? So they saved themselves $360,000. The cooling tower cost $150,000. So the geo system, it cost $360,000 for the loop, $150,000 for the tower. The total cost was $510,000. The original loop was $1.2 million. They managed to save $690,000 by utilizing a hybrid system. So through their winter months, they have free heat, and through the summer months, they have one of the most energy efficient systems available to the market.
That's significant, Dan. That's a big payday right there.
No, it certainly is. So when you're looking at options and, funding or, hey, it's out of budget, this is one option. So with variable or water source heat pumps, we do have options. We have a typical 2-pipe system. Well, it's a little over budget. Let's try a single pipe application. With a single pipe application, you're reducing your materials probably about 25 to 35%, and you're also going to reduce the amount of labor that you're doing on the install.
Sure.
And let's consider this full geo loop. It's out of budget. What other ways can we do by still utilizing this geo loop? Can we still want that 10% tax credit? There's ways we can do it.
Yeah, which is great. It doesn't have to be an all or nothing kind of deal, right? We can optimize for budgets and energy savings goals on a particular project and find that happy medium that works for that particular project. So,
absolutely. Now, I went through the systems very quick. In less than an hour. There's a lot more details into these systems, of course, of different components. But again, the goal here was just to get a base understanding of a water source heat pump system and its benefits and variations.
That concludes today's episode of Engineering Tomorrow and our Water Source Heat Pumps 101. A lot of great information there. And I would like to thank our experts for being on the show today, Dan Bilancia of ClimateMaster and Ryan Miller of Midwest Machinery, Kansas City. For more great videos, articles, and content, please visit engineeringtomorrow.blog. If you liked this episode or any episode of Engineering Tomorrow, please share it with your friends, your family, your cats, your dogs, your social media followers, your coworkers. That would be greatly appreciated. So until next time, keep engineering for tomorrow today.
Thanks for joining us on Engineering Tomorrow. If you liked the show, please take a moment to subscribe on iTunes or Spotify. For even more great engineering or construction knowledge, visit engineeringtomorrow.blog.